Hit it, Schwarz.
Go ahead, Ben.
Okay, I'm going to go ahead and get started. My name is Ben Schwarz, and I did a program over the slope construction method. I'm not going to go into all the details of this method, but this is something we learned back in Analysis 1. It's essentially a method of transferring moments through a beam or frame. And it's based on several things. The applied joint moments, so basically anything that you're adding to any specific joint, and the fixed-in moments. And then it's also based on the rotations of all your joints and if any joints have any deflection. Essentially, you're using one of these two equations. This is your equation for an internal span, or both ends fixed. You have modulus of elasticity, this constant, which is just the moment of inertia over the length. And then you have the rotations at each joint, your near end, your far end. You have, if there's a change in the, if there's basically a deflection over the span of the member, that's the change in angle of the member, and then fixed in moment added in there. You also have this equation in case you have a pinned end. So if one end's fixed and it's going towards an end that's pinned, you don't obviously have a far end rotation, so the equation changes a little bit. But essentially what you do for this method is you take these two equations plus any extra applied loads, and you just sum them on every joint, solve for your unknown rotations, and then refine your moments. And if you want to look more into this method, it's all in your Analysis 1 notes, and I explain this more in my user manual. So it's not too complicated. It's mostly just writing a lot of equations and doing a lot of algebra, which my program does for you. Now, my program can't do every possible scenario for this. It won't do frames. It only does just linear one end to the other beams. It only works for 1, 2, or 3 spans. As far as the end reactions go, they can be pinned, fixed, or you can have a cantilever applied to one of them, to either of them. And then all the internal reactions are just assumed to be rollers. And then as far as the loading in the middle, you can do a uniform load, or you can do one-point load or several-point loads. I'll do an example later of that. But all of these you can do with my program, multiple spans, certain types of loadings, and then certain reactions. Now, the worst part about this program is trying to input it. Obviously, Excel is not a 3D modeling program, so you can't just draw a beam on there. Essentially, the way you do that is with a series of user forms that sort of guide you through the process. And that's where I'm going to do an example to show you how it works. The first user form, you start by putting in your number of joints. You also put in your modulus of elasticity and your moment of inertia. However, this method, those just have to be constants. So your moments will always be the same no matter what your modulus and your moment of inertia are. It only changes what your rotations are. So those numbers don't matter so much. You can put anything in there and you'll get the same answer for your moment for the same beam. Then you basically go through a series of user forms that go joint by joint, and you do any reactions, what kind of loading, span lengths, that sort of thing. They won't warn you if you're doing things incorrectly, so that's why you have to be very slow and methodical going through these. But once you know what you're doing, it's a really simple program. You just go joint by joint by joint. And that's where I'm going to do an example to show you how that works. And then my user form has 2 sheets that it outputs on. On the first sheet, which I'll show you in a second, it basically reiterates what you've already input. So it tells you, here's the reactions you did, here's the loading, here's the spans. Everything you input goes into this sheet here, and I'll show you some more details on that. And then the second sheet gives you your results. Starts by listing the fixed-in moments, which you all know how to calculate, but it'll just do that for you. Then it lists all your K factors, which is, as I mentioned earlier, is just the moment of inertia divided by the length in inches. And then it gives you the rotation at all your joints, if it calculates those. And last, it just outputs your moments at every joint. So once you know how to set up your beam up correctly, it just gives you the answer. It's very simple. So with that, I'm going to go ahead and do an example. This is the example beam I'm going to do. It has 2 fixed ends, 3 spans, 2 of those are loaded. I'm going to have to take this off the slide, but I want to make sure that we go through this very carefully, so I'm actually going to draw out this beam over here, just so we have something to reference as we're putting this together. I would not recommend trying to do this program without having the drawing of your beam, because you'll probably make a mistake or forget a part of it halfway through. So it's very important that you know exactly what you need to be doing. Okay, so we have the first span has 2 kips per foot on it, the second span has no loading, and then the third span has 2-point loads of 9 kips each, and each span is 16 feet. And like I said, what you would do if you're not doing this with program is you would go to each of these joints and you set up that equation twice, one going each direction. Then you'd have to set up all the equations and then go back and solve for those rotations. So you could do this by hand. It would just take a little while, but it's a lot easier if you just input it in your program. So I'm going to go ahead and show you how to do that. Okay. So you create a beam. This is the first input user form that shows up. We select the number of joints. This includes reactions. It doesn't include cantilevers. So if we had an extension on one of these, we wouldn't include that, but we have 1, 2, 3, 4 joints. So. And then as I said earlier, these just need to be constants. Unless you're looking for the rotation specifically, you will get the exact same moment no matter what you put in these boxes. I'm just going to put in some numbers that seem pretty realistic here. Something like that. Now you basically read through your beam from left to right and go across it and input all the data as you go. So this first user form is about if there's any sort of cantilever on the first joint. We just have a fixed reaction, so there's no extension to the beam. I hit no. Now we're at the first joint. It's asking what kind of reaction is there. We have a fixed end. Then it's going to ask me about the span going to our right. So if there's any loading and what's the length of it. So I say that there's a uniform load. Its value is 2 kips per foot. And then we have a 15-foot span, to the next joint. Now we're at our second joint here. There is no loading. However, I need to fill in all these spots. So I just put a uniform load of 0, another 15-foot span, next joint. Now we're on our last span here. So on this one we have point loads. Their value is 9 kips, and we have 2-point loads. And the span once again is 15 feet. And now we're at our last joint. Our reaction is fixed. There is no extension. We hit finish. So on this sheet here, it basically, as best as you can in text in boxes, explains what we just did. No extension on the first, before the first joint. We have a fixed joint, 2 rollers, and then a fixed joint at the end. This is the type of loading. These are the distances. Joints, modulus of elasticity, moment of inertia. So to output all the information here, obviously I don't do that visually, but you can read through and make sure you did it correctly in case you're getting strange answers. Now we go to this sheet over here, and it gives our results. So these are the fixed end moments. From those 2, apply to each of those joints. This is the K factor for each span. These are our joint rotations, and these are our moments. And those are in kip feet. So we know that the reaction here is 49.5 kip feet. The internal moment here is 13.5. The internal moment here is 9. And the internal moment here is 40.5. So just like that, it gives you all your internal moments. One other thing is I wanted to make this as helpful as possible. So I use the notation we've been using in concrete, where negative moment is a downward curve, positive moment is an upward curve. So as you can see, I could draw out that these are curving that way at each of these joints. So now I know how I would design, for instance, a concrete beam or an E-beam. But that's basically how the program works. So, any questions? Yes?
Can you make you have 2-point loads, can you make them different in your program?
No, they have to all be equal, and they have to be equally spaced.
Concentric, okay.
So, and if you do 1-point load, it goes in the middle. I may try to add that later, but right now, they're all equal values and equal spacing for 1, 2, or 3-point loads.
And all moments of inertia are the same?
Yes.
Okay.
Modulus of elasticity and moment of inertia is constant throughout. Any other questions?